In this module, we're going to talk about forward kinematics of a robot device. The objectives of this module is to calculate the position of a point in a robotic device after multiple rotations and translations. And also, we're going to obtain the transformation metrics after using forward kinematics. So before we start to talk about forward kinematics, we would like to review a little bit about what is a homogeneous transformation we learned in the previous module. For homogeneous transformation, we are combining both rotation and displacement together. Let's work on the rotation a little bit more. So if we have two-dimensional case over here, and we try to identify what is the position using two-dimensional representation, instead of using single x component and y component representation as a vector, we try to represent everything using a matrix representation. So the basic idea is that we are having x component and y component as two column over here, but as a row we also have x component and y component. So what does this really mean? When we have a matrix like this, on this side we are talking about all xy components, but on this side we are talking about the new xy position. So if we have a position that is corresponding to the new axis x1 and y1, and we are having a specific position located over here and with an angle x and y. So if we projected this one onto the old xy coordinate system, the x component over here is actually cosine theta, y component is sine theta. For the y components over here, it is actually a negative sine theta. This is sine theta, and this is cosine theta. When we look at cosine theta and sine theta over here, we are actually talking about the unit, one unit along this direction and one unit along this direction. So when we project the unit vector of x component and y component from the new coordinate system back to the old coordinate system, this is how we're going to represent that. So cosine and sine is easy and straightforward for us to understand what's going on. But if you are rotating the coordinate system with a 90-degree angle, like this figure shown over here, then it will be easier and more straightforward that we can just generate the matrices directly. So if we are talking about we are rotating the theta is actually 90-degree, then the projection is going to be pretty straightforward, because the y1, keep in mind we are having xy component over here, we will have all xy component over here. So if you rotate like 90-degree, 180-degree, 270-degree, then it would be easy for us to determine what this matrix is going to look like, because we can simply find out what is a unit vector along individual axes and project that to the coordinate system and determine where we should put one component over here. So in this case, y1 is along the direction of O x naught. So the y1 component is actually over here as 1. And this part is of course 0. And the x1 component is moving is actually lying on the direction of negative y0. So the rotation matrix is actually look like this, which should be pretty straightforward for us to come up with um, the the transformation matrix R. Now, if we expand everything into three-dimensional space, then what are we going to do? First, we would like to talk about the right-hand rule. The right-hand rule is to help us to determine which direction is x, which direction is y, and which direction is z. So if we are using right-hand rule, the sum is always our z direction, the index finger is always our x direction, and y direction is our middle finger. With those kind of idea, then we can determine how to rotate everything easily, and we can determine which direction should be x, y, and z when we make a rotation. So if we do not have any rotation, which means my theta, my phi, my psi are all zeros. It is clear, when we do not have any rotation, the unit vector is certainly along x direction, x naught direction, y naught direction, and z naught direction. So we put one over here, one over here, and one over here. And those three ones are our unit directions, unit vectors. So the other components, we can just fill that with zeros. And that is how we're going to um, determine the transformation matrix. If we rotate that with along a specific direction, then, for instance, if I rotate 90 degrees about y0 direction, the new coordinate system is going to be look like this. Since I'm rotating about y0 direction, y1 remains along the same direction, but the z0 direction is going to be rotated from this direction to this direction. So this is going to be my z1, and x0 has been rotated from this specific direction to the downward direction. So the new coordinate is going to look like this after 90 degree rotated about y0 direction. With the technique we learned just now, the y1 still the same direction as y0, so we still project it onto the old coordinate system and obtain this number over here is 0, is 1. This is 0, this is 1, and this is 0. For the x1 direction, it actually projected onto the negative z direction. So we're going to have negative 1 over here. The other direction, we are having zeros over here. For the z direction, instead of projected along z naught direction, it becomes projected onto x naught direction. So we're going to have 1 over here and 2 zeros over here. So this is going to be my transformation matrix from R0 to R1. If we further rotate this one into another direction, let's name this one 2, 2, and 2. So this time we are rotated about the new z1 direction with 90 degree. So when we do something like this, our y1 is actually from this direction to the new y2 direction, and our x1 direction is also be rotated with 90 degree angle from this x1 direction into x2 direction. And if we try to determine the transformation matrix from frame 1 to frame 2. Then we are checking back. We are comparing those two coordinate system or those two frames to determine where we should put 1 and where we should put zeros. So since we are rotated about z direction, which means the z should have the same coordinate system, which we have 0 in the x component as our x component, 0 as our y component, and y as our z component. This time, x2 has been projected along the y1 direction in the positive direction. So we're going to have 1 along the y direction, 0 along x direction and z direction. Go back to this coordinate system over here. This time on my y2 is actually along this new direction. So I'll have -1 and 0, 0. So this is going to be my new transformation matrix from this coordinate into this coordinate. So we might want to know if I actually try to convert from R0 to R2. This time is going to be R0, 1 multiplied by R 1 to 2. So if we have this matrix multiplied by this matrix, we have 0, 0, -1, 0, 1, 0, 1, 0, 0, multiplied by 0, 1, 0, -1, 0, 0, 0, 0, 1. Then we are going to get our system or our transformation matrix that is going to be 0, 1, 0, 0, 0, 1, and 1, 0, 0. So this is going to be our R0 to 2. Convert from frame 0 to frame 2. So this should be pretty straightforward. You can just multiply those two transformation matrices together, or you can actually try to identify, compare the coordinate system of the original one and the second frame over here. You're going to find out x2 is actually projected along the y0 direction, so we have one unit vector on the y direction, and the other two axes are going to have their corresponding unit vector at the specific location. So either you use the multiplication of matrices, or you can use the projection method. So we can determine the transformation matrix in either way.